Hello everyone, my name is Sebastian and today I'm going to be talking about predicting the resilience of code obfuscation against symbolic execution attacks using machine learning. This is joint work together with Christian Collberg from the University of Arizona and my supervisor Alexander Pretschner from the Technical University of Munich. So for those of you who are not familiar with what obfuscation does, it transforms a program P, which contains some hidden secret data or secret algorithms, into a program P prime, which is more difficult to understand. So this data and the algorithms are hidden somehow. The opposite process of extracting this hidden data and the algorithm is called reverse engineering. And the goal is not necessarily to extract the original source code, but it could be just the data or just a control flow graph. In IT security, you have several attacker models, such as man-in-the-middle attacker, which tries to intercept communication between two parties and compromise integrity, confidentiality, and so on. We have remote attackers, which try to exploit software running on remote servers using buffer overflow exploits and so on. And we have man-at-the-end attackers, which receive software from a software vendor, and they try to reverse engineer it in order to extract secret data or intellectual property. In this talk, we're going to be focusing on the third type of attacker. So obfuscation aims to defend against only this type of attacker. And the problem in this context is that you have a software developer who wants to protect his program for a certain number of days, and given that there are dozens of obfuscation transformations out there, he's confused. So he doesn't know which ones to use in which combination in order to achieve this goal and solve this problem. The current approach towards this problem has been proposed by Hefner and Collberg a while back, and it's called the obfuscation executive. And this obfuscation executive takes an original program as input and a certain performance overhead which is tolerated, and it outputs an obfuscated program which satisfies this constraint. Now the defender, what he can do afterwards is take this obfuscated program and try to run the automated deobfuscation attack and see if it can, if the obfuscated program can withstand the attack for 100 days, and then he's done, right? But if not, then he has to go back and ask the obfuscation executive, give me another obfuscated program, and then go back running to run the attack. So this could take a while, this loop. Therefore, we propose a faster approach, which builds on top of the obfuscation executive, and we say that based on the obfuscated program features, we can predict the time necessary for a deobfuscation attack. And this loop from the prediction to the obfuscation executive is much shorter than it would be to actually execute the attack and wait for 100 days or so. Now, the research questions which we want to answer in this paper, or which we answered in this paper, are that how can we actually do a prediction of the effort needed to deobfuscate a program using these automated reverse engineering attacks? Which features are important for predicting the time needed for such an attack? And we performed a case study on symbolic execution. Therefore, in this paper, we give the features which are relevant for symbolic execution. And thirdly, we want to see if there is a big difference between different regression algorithms used to perform this prediction. We propose a methodology consisting of 5 steps. This methodology is generic, and first step is to create a large data set of programs that are used for training. Afterwards, we obfuscate these programs, and we attack them using an automated deobfuscation attack. We also extract the features from these obfuscated programs, and using the features and the time needed for the deobfuscation attack, we create the prediction models needed for the obfuscation effort. We instantiate this methodology on the obfuscation attack based on symbolic execution, which we presented in a previous paper. And for those of you who are not familiar with symbolic execution, it basically is a program analysis technique where you take a certain program, have a very simple C program here, for example, and instead of using concrete values, we use symbolic values. So in this case, consider A, B, and C as symbolic input values, which are processed by the program. And symbolic execution basically interprets each instruction, and whenever it encounters a branch, it forks into on each path of the branch, gathering certain path constraints along the way. At the end of an execution path, these path constraints are sent to an SMT solver, which tries to find a certain assignment to all of the variables, and if it is able to find an assignment, you now have an input which can take you along that path in the code. So based on symbolic execution, you can see that you can use this attack or this programming analysis technique to attack license checkers. So you can bypass license checks by taking an input program as the one shown here, and if you mark the input to this program as symbolic, this program computes a certain function f on the input and provides a certain output which is compared to a constant value, and this simulates a license check. If the license check is passed, then your game starts or you have access, and this is symbolized here by printing you win. Now, you input this program to a symbolic executor, and it searches for the path that would get you to this printf statement, you win. After it finds the path, it sends the path constraints to the to the SMT solver, and the SMT solver tries to solve it, and then it outputs your license key. Now, this paper basically aims to compute a model that can predict the time needed to perform this attack on any given program. So back to our methodology, the first step was to create a data set of programs, and if you're trying to do machine learning, you need a large data set of programs. Since it's not that common to find open source programs that have license checks in them, another approach could be to take some open source programs which do not have license checks and manually place in the license checks. But this is a bit, it's not scalable to a large data set that you can do training on. Moreover, what we noticed is that attackers don't symbolically execute large programs, but they pinpoint a certain part of the program which is interesting, and then perform symbolic execution on that small part. So using a large program, putting a license check into it would not necessarily lead to a good evaluation. Therefore, what we thought was, let's identify some features which are relevant for symbolic execution, such as the range of symbolic variables, control flow structure, if the control flow is based on symbolic variables, branches, and types of operators. And then let's generate a data set which is representative using various values for all of these features. So we wrote a C program generator which generates programs having this structure, a similar structure to this program shown on the right side of the slide. You have an expansion phase where the inputs are expanded into several state variables. Then you have a mixing phase where all of these state variables are processed using different types of operations. And finally, you have a compression phase where all of the state variables are merged into the output variable. And this randomly generated function is used in the main function below as sort of a hash algorithm which processes the input, and then the output of the hash function is compared to a constant value. If they are equal, then the desired logic is executed, so uwin is printed. Our generator has several parameters, and for our experiments we used these 6 parameters. In parentheses after the name of the parameter, I have how many different values we used for each parameter. So for instance, for data types we used 4. We used char, short, int, and long data types. And for the other parameters, we also use different values, which are detailed explained in detail in the paper. And in total, the total number of programs we generated is obtained just by multiplying these values. So it's around, it's exactly 4,608 programs, which have different sizes and complexities. So we obtained this data set, and now we want to obfuscate each program from this data set. And we use the Tigris obfuscator, as the previous work also did. We use these 5 popular obfuscation transformations. Virtualization was explained in the previous talk. Flattening is a control flow flattening. Opaque predicates. Encoding arithmetic is a variant of mixed Boolean arithmetic, and encoding literals basically destroys constant values, creating procedures which recreate these constant values at runtime. By obfuscating each of the programs obtained in the first step, we obtain a bit over 23,000 obfuscated programs, which in the subsequent step we attack using the symbolic execution attack of extracting the license key from each of these programs. And we recorded the time needed for each of these attacks. In parallel, we also extracted program features from these obfuscated programs, and in total we had 64 features, including static code features such as cyclomatic complexity, number of lines of code, and so on, dynamic code metrics such as memory usage, execution time, and so on, and SAT metrics. Now you may be wondering, what are SAT metrics? Well, they're graph metrics on SAT instances which are represented as graphs. So if you have this SAT instance shown here, consisting of 3 variables, x, y, and z, you can represent it as a graph, as shown here, where an arc between 2 nodes represents a disjunction, and a node represents a variable, or a negation of a variable. So you may be asking yourself, so how does a SAT instance look like for a real program, right? So if you take a non-cryptographic hash function, such as the one shown on this slide, and you compute the SAT instance corresponding to the path constraint leading to the statement you win, then you obtain this SAT instance where the yellow dots represent nodes and all the other colors represent arcs. Now, if you execute the symbolic execution-based attack on this instance, an SMT solver will solve it in about 7.5 seconds. However, if you apply obfuscation, some strong obfuscation transformations such as virtualization and a control flow flattening, then you obtain a much more convoluted SAT instance where these community structures in the previous picture disappear. So everything becomes much more dense and is therefore harder to solve. So there exists some related work in the SAT solver field, which says that if you are able to destroy community structures in the SAT instances, then the SAT instances become harder to solve. Therefore, we conclude that strong obfuscation transformations destroy these community structures. After we obtain the features and the times needed for attacking, we can go on to building our prediction models. However, given that you may have a lot of features, we have 64, but let's say there are a lot, we want to narrow down this number to less features which are relevant for our prediction model. So using recursive feature selection, we were able to drill down to 15 important features out of the 64 that we computed. And we plotted these top 15 features according to their importance. And we noticed that from the top 15, 13 are SAT features, and only 2 of them are static code features related to cyclomatic complexity and the number of loops. All other features are SAT features, and this is because most of the time spent by symbolic execution is solving the SAT instances. So most important features are SAT features, and these correspond to the complexity of the path constraints which you have in your program. So if you have programs which perform more complex computations, then the time needed by the SAT solver increases. Afterward, we employed 4 machine learning algorithms for building these prediction models. Neural networks, which are very popular nowadays, support vector machines, random forest, and genetic programming. And we obtained the following results. On the horizontal axis, you can see the percentage of programs in our data set, and on the vertical axis, you can see the relative error of prediction. So here we're trying to predict how much time does the symbolic execution attack need to break a certain obfuscation. So you can see that for 5%, for this 5% of our data set, the prediction error is very low, and it increases as we consider more and more samples from our data set. However, even for 85% of the programs, the maximum error, which is plotted with a solid line, is below 15%, and the median error is below 10% even for the entire data set. So we believe these results to be encouraging. However, the question probably on everyone's mind is, do the results generalize? Because we've basically created a synthetic data set using our C code generator, where we varied certain parameters, and we tried 5 different obfuscation transformations. However, does this generalize to other programs which are not synthesized by our code generator and maybe applying multiple layers of obfuscation? So that's exactly what we tried to do. We collected 11 popular non-cryptographic hash functions, and we used these hash functions as license checkers instead of our randomly generated functions, and we applied 2 layers of obfuscation instead of 1. So we had 5 obfuscation transformations, and we said we apply all the combinations of these 5. So in total we had 25 times 11, 275 programs. And we applied the prediction model trained using the random programs on these 275 programs. And the results we obtained were also encouraging, because for about 85% of the programs, of these 275 programs, the prediction error was still below 15%, the maximum error I'm saying here, and the median error was quite low. We also removed outliers. We removed 10%, 4%, and 0%. The more outliers we remove, the higher the error gets because of the normalization. We went further than that, and we collected 11 instances of cryptographic hash function from the SAT competition. These cryptographic hash function instances are built such that they can be broken by state-of-the-art SAT solvers, because state-of-the-art cryptographic algorithms cannot yet be broken by SAT solvers. However, we took the top 10 SAT features that we obtained in our previous experiments, and we trained a random forest model using these features on our randomly generated C programs. And then we applied this model to the SAT instances corresponding to the cryptographic hash functions. And the results are displayed in this table. So we had 11 hash functions, which we could not obfuscate because they're just SAT instances. They're not C programs, sorry. And the solver, the time that the solver took is displayed in the second column, and the time that we predicted is displayed in the third column. The ratio between the two is on the last column, and the ratio closer to 1 is better. So we see that the ratio may be off up to a factor of 4.5. However, we believe that this is still encouraging given the fact that our randomly generated functions, our synthetic functions, are as far from cryptographic hash functions as can be. So we believe there's still work to be done in finding better features. However, still this may be a good approach. To conclude, I want to say that we proposed a general approach towards the obfuscation effort prediction. We created a C code generator, which we used to generate over 4,500 non-obfuscated C programs. We obfuscated each of these programs to obtain a data set of over 23,000 obfuscated programs, which we used in our case study to employ a deobfuscation attack based on symbolic execution. And we observed from our experiment that SAT features are most relevant for predicting the effort needed by these symbolic execution attacks. The different machine learning algorithms that we employed for building these regression models are do not differ a lot. We've noticed certain levels of improvement by using different machine learning algorithms. However, the core point is the features and not which machine learning algorithms you employ. We also trained using synthetically generated C programs and applied this to cryptographic and non-cryptographic hash functions, and we obtained encouraging results. In future work, we want to apply this methodology to other state-of-the-art deobfuscation attacks, such as control flow graph simplification, disassembly, and even synthesis, which was presented in the previous talk. And we want to extend our benchmark generator to create more representative samples of programs. We also are interested in applying machine learning to directly extract more features and not just use existing tools for feature extraction. So the big conclusion in this work is that features are the key point to prediction, and therefore we need better features because the error is still there. There is an error. We open sourced the dataset and the scripts, and the C code generator is freely available. And with that, I would like to conclude my talk, and thank you for your attention.
Yeah, question. Hi. Doesn't work. Hi, nice talk.
Thanks.
Regarding SMT solvers, I observed that different SMT solvers behave completely different for different formulas regarding time. So, for instance, if I have something as quantifier theory of bit vectors and arrays, Bulector takes just seconds, while Z3 takes hours, and things like that. So, did you compare it with different SMT solvers, and how do you know, for instance, if you change minor things in a symbolic formula, an SMT solver may behave completely different? So, how do you tackle this?
So that's a very good point. I didn't actually compare different SMT solvers. I mainly relied on the SMT solver used by CLI, which is STP. However, this is definitely a prediction. So the predictions that we have are specific to the implementations, let's say. So if you want a very close or good prediction, you need to know which is the state-of-the-art attack, which is the best, and then you should compare, or you should benchmark your program against that and not use, let's say, you don't need to use all of the existing ones, right? You're interested in the best one, and then if you're able to withstand the attack for 100 days on the best one, then you're good to go, right?
Well, regarding SMT solvers, there is no best one in that case. Basically, what I do is I just run n SMT solvers in parallel, and the first one that terminates. So the problem is I don't think that you can do it such easily, because
you're right. You're right. So indeed, there's no best one in general, but there's the best one for your given program, right? So if you want to you have a certain program that you want to defend, and that program is the one that you should find the best one for. That's what I'm saying.
Yeah, but not necessary. So if you just change minor things, the one SMT solver may be better, and if you change another thing, the other SMT solver is better. So I don't think that you can generalize it in this way.
Okay, yeah, you're right. So I agree that if you start changing stuff, then you to your original program maybe, right? Then you need to rerun the training and build a new prediction model. But what I'm saying is that given that you have a certain logic that you want to keep, then I think you can build such a prediction model.
Mm-hmm. Okay, thank you.
You're welcome.
Any more questions? Okay, let's thank speaker one more time.